geometry and investigates how viscosity approximation based. My screen is visible, sir?
No, ma'am, not visible.
Now it is visible, I think. Hello? I think it is visible now.
No, ma'am, not visible.
Just a minute. Now it is visible. Hello? Is it now?
No, ma'am.
Just a minute. I hope it is now.
Yes, ma'am, now it is visible.
Yes.
Yeah.
Yes.
Yeah, now it's visible.
Yes, sir. Okay, sir. So our work explores the fascinating intersection of complex dynamics, fixed point theory, and fractal geometry, and investigates how viscosity approximation method can be utilized
Make it a
to
full
generate
screen.
and analyze Julia sets
Please,
with
please
improved
make it a
stability.
please make it a full screen.
Yes, sir, it is full screen. On my screen, it is full.
Okay.
Haha. I hope you are able to see.
Okay. Now it's okay. Now it's okay.
Yeah. Yes, sir. Yeah. And investigate how viscosity approximation method can be utilized to generate and analyze Julia sets with improved stability and convergence properties. Next, in introductory part, I would like to present some introductory terminologies. Julia sets. So Julia sets are among the most beautiful and mathematically rich objects in fractal geometry. They arise from the repeated iteration of non-linear complex functions and reveal intricate structures exhibiting self-similarity and chaos. Traditionally, Julia sets are generated using classical iteration schemes such as Picard and Mann iterations. However, when dealing with highly nonlinear mappings, these methods may suffer from convergence instability and limited boundedness regions. So to address these challenges, we introduce viscosity approximation methods inspired by the work of Modafi and Mange into the framework of Julia set generation. Our objective is to improve convergence behavior while preserving the rich fractal structures associated with complex dynamics. Next, generalized logistic map and viscosity iteration. So the foundation of this work is the generalized logistic map introduced by Davish and Tanvir. The map is given by f of z is equal to r into z multiplied by s into s minus z raised to m, where m is positive integer greater than equal to 2 and r and s are complex parameters, where r not equal to 0. So instead of directly iterating this function, we employ a viscosity iteration process. The viscosity orbit is defined through two stages. First is yn is equal to lambda into zn plus 1 minus lambda into f of z. And second is zn plus 1 is equal to alpha into z of zn plus 1 minus alpha into yn. Here g of z is equal to az plus b is a contraction mapping where modulus of a is less than 1. while parameters alpha and lambda are control parameters. This additional contraction component GZ act as a stabilizing force, reducing oscillations and improving convergence characteristics. Next, so in escape criteria, we have derived this result, which is visible on the screen. You can see. So an important theoretical contribution of this work is the derivation of an escape criteria. We proved that if the initial point lies outside a specific radius capital R, then the viscosity of the orbit diverges to infinity. So this theorem provides a bounded computational region containing the entire viscosity Julia set. From a practical perspective, this significantly reduces computational cost because points outside the escape radius need not to be determined further or examined further. So therefore, the theorem not only strengthens the theoretical framework, but also improves computational efficiency. Next is the algorithm. I hope the screen is visible to you. So in algorithm part, using the escape criteria, we developed an escape time algorithm. The procedure is straightforward. In first step, we compute the escape radius capital R, and then we select a starting point Z0 in the complex plane, then applying the viscosity iteration repeatedly, we check whether the orbit escapes, and then we assign colors according to number of iterations required for escape. The resulting color distribution reveals the complexity of the fractal boundary and highlights the subtle dynamical behavior. So these algorithm forms the computational backbone of our study. In next slide, we see various effects of the parameters. So here actually there are 4 parameters, M, R, lambda, and S. So there are 4 cluster of figures are visible in the slide. So one of the most interesting aspects of this research is observing how these parameters influence the geometry of the Julia sets. In first cluster of figures, we see that when the exponent small m increases from 4 to 7, the number of fractal arms increases correspondingly and produces flower-like structures with higher rotational symmetry. Of course, in figure we have shown it for 4, 5, 6, and 7 values of m. In second cluster of figures, we see that the imaginary part of parameter R controls rotational behavior. Small values generate clockwise twisting, while larger values produce counterclockwise spirals. Whereas in the third cluster of figures, we see variation in viscosity parameter lambda expand or contract the basin of attraction, thereby affecting density and sharpness. And in the fourth cluster, we see that changing the parameter S produces dramatical transformations, including disconnected components, triangular shapes, and tightly wound spiral structure. So these observations demonstrate the remarkable flexibility of viscosity-based dynamics in generating diverse fractal morphologies. Now in next, numerical research, that is AET and NAI. So quantitatively analyze the generated fractals, we employed 2 metrics. that is average escape time, that is AT, and non-escaping area index, NAI. AT measures how long points remain bounded before escaping, and NAI measures the proportion of points that remain bounded within the computational domain. So NAI reaches 1.0 when AT equal to 0, conforming entire domain is non-escaping. In next slide, we see the analysis when lambda and alpha are varying. So we also examine the interplay between the contraction parameter lambda and the viscosity parameter alpha. So several threshold values were identified where sudden changes occur in both AT and NAI. So this transition resembles bifurcation phenomena commonly observed in nonlinear dynamical system. Such threshold behavior indicates that viscosity parameter can effectively regulate the balance between stability and complexity. So these provide researcher with a useful mechanism for controlling fractal evolution. So NAI increases with alpha, reaches 1.0 at alpha greater than 0.9 something for lambda equal to 0.86, which is visible in this figure. Now in next slide, we extend the analysis to the complex parameter plane associated with parameter S. The resulting AT and NAI maps exhibit structure remarkably similar to Mandelbrot-like regions. So high AT region form Mandelbrot-like shapes and minimum AT 1.0 near origin, which shows fastest escape. In the figure, we have shown it for m is equal to 4 only. We have skipped showing here for m equal to 7 and 3. Now in next slide, we see spatial maps in the complex parameter plane. That is Picard vs Mann vs viscosity. So key findings here we see that the analysis to the complex parameter plane associated with parameter S and the resulting AT and NAI maps exhibit structure remarkably similar to Mandelbrot-like regions. High AT regions correspond to complex bounded dynamics, whereas low AT regions indicate rapid convergence. This spatial map provides global perspective on parameter sensitivity and reveal how different regions of parameter plane influence fractal behavior. In this slide, a central objective of this work was to compare viscosity iteration with classical methods, that is Mann and Picard. So compared with Mann and Picard iteration, we see that viscosity iteration achieves significantly high NAI values. Secondary thing is average escape time are larger, which indicate broader bounded regions. And convergence is approximately 15 to 20% faster for higher order systems. Also, generated factors exhibit richer and more anisotropic structure. So therefore, these findings suggest that viscosity iteration offers a superior framework for exploring complex dynamical system requiring enhanced stability and control. So viscosity iteration is ideal for application requiring
Hello? We can't see the screen and hear the voice. You can see the screen has stopped and we can't hear you.
हम क्लोज कर
I think so.
वो तो है यार पंत इज नॉट पिकिंग अप ऑन
Okay.
स्विच ऑफ आ रहा Namaskar, so we can conclude this online session. And Professor Abhinand Pant could not be due to some network issue or some other issue. So we thank to both of the speaker, Professor Jain Singh and Professor Darshana Prajapati ji, for delivering such a wonderful and knowledgeable talk in this conference. Also, we thanks to our chairperson, Professor.
Hello.
I
Hello,
request.
sir. My voice is audible.
Yeah.
I hope I have presented the work and it is audible.
Yeah,
To all.
yeah. Now I think
Who is she?
Yes, sir.
Actually, we are concluding this session due to shortage of time. Our next speaker is waiting for the lecture. Is it Jain Singh? So we would like to thanks to our speaker for delivering such a wonderful lecture in this international conference. And we appreciate their efforts. And we, on the behalf of VPI and organizing team, I'm very much thankful to both of them. Thank you.
Thank you, sir.
Also, I would like to thanks to our chairperson, Professor A.P. Singh, for conducting this online session. I request Professor C.S. Christie to hand over the memento to the Professor A.P. Singh.
प्रेजेंटेशन बोर्ड पे भी मैम आप एक बार चेक कर लें सोलर सोसाइटी ये जहाँ पे आपको ठीक लगे सुटेबल आपके
ये तो
ओके एक बार चेक कर लें
hello am I audible hello 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 I think audible है
हाँ
है ना?
ठीक है ऑनलाइन के लिए भी ऑन है
should I start
यस मैम चल रहा है ऑनलाइन चल रहा है नहीं वो लिख रहे मैम की पीपीटी
शेयर करना
शेयर करने ना उसको यस मैम
So, good morning, esteemed chairperson, ma'am. SL Singh, sir, in my memories, and worthy audience, a very good morning to all present here. And thank you, organizers, especially Garola, sir, for giving me this opportunity. Today, I want to take you to the journey through the mathematical foundations that makes mathematics has made so much of powerful. It is not only powerful, if I am using the explainable artificial intelligence, it is explainable, but with the help of mathematics only. So explainable at its core, AI is a mathematical function like simply f from x to y. F maps input from some space x to a decision space in y. The question what we will explore today is, can we understand why this mapping produces the decision and how these decisions are explainable? In general, if I am taking a mapping f from x to y, that is simply decisions we are taking. But if we want to make it if we want to make it explainable, then we need the pillars of mathematics. So that question is the heart of explainable AI, and mathematics is the only language that is precise enough to answer it. So why we need explainability when we do the artificial intelligence, especially deep learning programs? Consider a standard deep learning model. Here we are giving input parameter X, then the network applies its some parameters and train the model and give us a model. And then it comes out with a prediction. It set up some parameters theta, then it takes the input value X, applies some parameters theta, and this pass through the network model and gives us certain decisions. But those decisions are simply black box. Black box means they'll give us simply the decision, but they'll not tell why these decisions have come. What is the reason behind it? So maths could answer it. So, but the reasoning is completely hidden. Look at this pipeline of the deep learning model. It inputs some input, then it passes through the neural network. It takes the decision. Then there is a question mark. That golden block is simply what after that, whether the decisions we are taking, whether they are trustworthy, whether they are fair, whether there is any accountability for that, or is there any safety associated with that. So this problem is like in high stake domains, black box model, deep learning model in general is a black box model which do not explain anything. So the trust collapses when the user cannot understand why a model has flagged something Hidden biases may discriminate against protected groups. Then there is accountability. This fails under regulations like GDPR that legally require justified decisions. And above all, the safety. This safety is compromised, especially in defense application where we cannot diagnose why a system is failed. We need to know why the system is failed. So the challenge is not prediction accuracy alone. It is understanding why this such prediction has been made. So let us formally define what we mean by intelligent decision system. Mathematically, it is simply D equals Fx, a function that takes data and produces a decision. But the architecture is richer in that. Data feeds into the learning component, which builds a model. The model runs inference, then decisions are made, and critically, an intelligent decision system is made. But that decision must come with an explanation. So that final golden block in the pipeline is what separates a block back. Up till this decision, this is simply a black box. So this golden block explanation differentiate it from the black blocks architecture. This architecture is actually not only hypothetical. This is already existing in market. For an example, it is deployed in the healthcare system where diagnosis and treatment decision, they are well explained why this diagnosis has been made and why the certain decisions are, why this treatment has been prescribed. In cybersecurity, we are using the explainability model for the threat detection. In finance, for credit and risk assessment, we are using, and especially in defense, for the autonomous decision support system. In every one of these domains, the cost of an unexplained wrong decision can be dangerous. So whatever the decision we are taking, that should be explainable. So the mathematical pillars of this whole architectures are linear algebra, probability theory, statistics, optimization, information theory, and game theory. So there are 6 pillars which underpins all of this study. Linear algebra gives us the matrix operation that power every neural network. So neural network is nothing, just the combination of matrices where somewhere they are multiplying, somewhere they are editing, etc. So linear algebra is a very powerful tool which gives all the operations. In all the middle layers of deep learning, we are applying the concepts of linear algebra. Then we have probability theory. Probability theory gives us powerful Bayes theorem, which reasons under uncertainty. Uncertainty means because the deep learning model, they work on the uncertain data. So when we are using the Bayes theorem, it reasons under uncertainty. After that, statistics tools give us the tools to validate and interpret the models. How we are validating the whole model and how we are interpreting the model. Then the optimization theory. This is very important in deep learning. Optimization theory is a very powerful gradient descent algorithm. Gradient descent algorithm, which we'll also discuss in detail after that. Optimization theory, gradient descent algorithm that train them. So the whole neural network architecture is trained with the help of gradient descent algorithm. Although there are other variants of gradient descent, but at its core, gradient descent algorithm is being used to train the whole neural network. After that, we have information theory. Information theory gives us the entropy. What entropy does, it gives us the measure of uncertainty and the information content. Measure of uncertainty means, and the information content, how much information is being contained in that architecture, in that whole model. And lastly, the game theory. Game theory, that actually its applications are vast, but due to explainability, it has recently come into in detail right now. So in game theory, perhaps surprisingly gives us the most mathematically principled framework for explaining the features. Explaining the feature contribution, because neural network is the combination of features. So what is the importance of each feature that this game theory gives us? So shortly, these 6 pillars form the mathematical foundation from which AI and explainability emerge. The flow is simple but profound. Mathematics enables AI enables explainability, and explainability enables trustworthy decision system. So we'll just go through all these 6 pillars in a just a little bit of detail, not much, just little bit. So the linear algebra and deep learning. So let us begin with the fundamental operation, this linear algebra. The whole neural architecture is just Wx plus B, where X is my input, W is the weighted matrix, and B is the bias which is being introduced in the network. So it computes Y output decision as Wx plus B. W is the weight matrix, X is input vector, B is the bias. So in deep network, this is the forward propagation. The activation layer, there is an activation. These are hidden layers where we'll just do this simple computation. Then there is an activation layer which introduces non-linearity in the model. And then summation, weighted summation is applied to this output, which gives us the final output. So this means that the deep networks are learning hierarchical mathematical transformation. All the intermediate layers in the deep learning, they are nothing, just the mathematical transformations. At each layer, we are using some or other mathematical transformation. So in early, or basically in deep learning, early layer, they detect simple patterns. Like if I want to find out something from an image, then the early layer, they find out some simple patterns like edges, frequencies, etc. And then the deeper layers or the more advanced layer, they find out the complex features. So if we add on further explainability into this, they'll find out which features are more important and which are needed, and what is the contribution of each feature. So when we want to explain a deep network, we are essentially asking which of these transformations contributed most to the final output. So that is the linear algebra at its core. Then we have optimization and gradient descent. So how does a network learn those weights? That is through optimization. Here, with the help of optimization theory, we define a loss function. Loss function means what is the difference between the predicted output and the calculated output. The difference is loss, and we want to minimize that loss. That loss is being overcome with the help of optimization theory, and for that we use gradient descent algorithm. So we define a loss function L of theta, and our goal is to find the parameter theta star which minimizes it. The algorithm that achieves this particular loss function, minimizes this loss function, that is gradient descent. At each step here, we update our parameters by moving in the direction opposite to the gradient, scaled by learning rate eta. So this is my previous calculation, previous iteration, and this is my loss function. And delta loss function, I take the differentiation of loss function and apply eta times of this loss function, and that will be my next iteration. So at each iteration, I'm just improving my previous output. So this eta also controls the learning rate. This similar we do in the mathematics, like in Picard iteration or superior iteration, where by setting the value of eta, the parameter, we control the rate of flow. So every classification, prediction, and decision-making model we encounter has been trained through some variant of this gradient descent algorithm. After that, we have this probability and information theory. Two more pillars which are essential for the explainability, they are probability and information theory. Bayes' theorem tells us how to update our beliefs given the new evidence. So because whenever we have some new evidence, we have to change the probability, posterior probability, depending upon the prior probability. So the posterior probability of given A equals B equal likelihood the times the prior, means given the prior probability and we calculate the posterior. So I think this all we know. Then we have how to measure the entropy. This function is given by Shannon entropy. With Shannon entropy, h of x is equal to minus sigma pxi log pxi. This gives us how much information is being contained in that particular model or in that particular information. So when entropy is maximum, the system is completely uncertain. And when the entropy is zero, the distribution is certain. Entropy appears everywhere in explainable AI, in decision trees, in information gain, and in measuring the confidence of explanations. Then we have the explainable AI framework. So now we have gathered all the mathematical ingredients. So now let us assemble them into a formal explainable AI framework. The goal is no longer just to compute f of x, but we want to explain f of x. The pipeline has 4 stages and input. It flows into the prediction model, which is then passed to an explainable engine whose output produces the human understanding. The explanation engine is where the mathematical of explainable AI lives. There are, in general, for explainable AI, there are 4 features or 4 methods, principal methods, namely SHAPE, LIME, attention mechanism, and counterfactual. SHAPE is grounded from the game theory. LIME is built through the local linear approximation. Attention has come through the transformer models and saliency maps, and counterfactual has come from the minimal change analysis. So what is the Shapley value attribution? The SHAPE means the Shapley additive explanations. That is the most mathematically rigorous method in XAI, explainable AI. This is the formula where we sum over all possible subsets that do not include that feature I and measure how much the prediction changes when we add that particular feature I to that subset. So this comes directly from the cooperative game theory, where the players are features and the game is the prediction. So what makes this Shapley value special is that they satisfy 4 fundamental axioms: efficiency, this contributes some to the total model output, symmetry, that equally important feature should receive equal values, dummy, irrelevant features should have 0 value, and additivity means this is the combines across the models. Then the next we have LIME attention, LIME attention and counterfactual. LIME is local interpretable model agnostic explanation. In this, instead of using the global explanation, suppose our output model is quite complex, then we just approximate it through a simple model. So here F is my output model, which I have got through my deep learning model, and I'm approximating it through a simple model G. So F is locally, the optimization minimizes this fidelity loss between F and G in the neighborhood defined by nu x. Okay, then we have attention mechanism. This from the transformer architecture gives us a third approach. The formula computes the weighted combination of value vector V, where the weights come from the scaled dot product. And in the last, we have counterfactual explanation. What is the minimal change to X which will flip the decision? That means if we minimize the distance to a new point X prime subject to the model outputting to a different label, means whenever there, what a slight change in X will flip the decision. And in the last, this fairness and robustness, explainability alone is not sufficient for trustworthy. We also need mathematical guarantees of fairness and robustness. Statistical parity requires that the probability of a positive prediction is equal across protected groups. A equals 0, A equals 1. This is formal mathematical definition of non-discrimination. It applies to some of the existing theories also. It applies to hiring, lending, healthcare, any domain where an AI decision affects people's lives differently based on group membership. It gives robustness formalized through the Lipschutz condition in mathematics. Lipschutz condition is like whenever there is a small change in the input, then how much changing in the output. So it controls the stability through the Lipschutz criteria. Okay. And then an explanation that is sensitive to tiny perturbation is not a reliable explanation. And looking forward, the most exciting frontier is causal explainability. Okay, so what are the applications in intelligent decision system? We only accept those decisions that can be justified. Otherwise, we can simply ignore them because they can be dangerous. For an example, in healthcare, XAI explain why a model recommended a particular diagnosis or drug, enables doctors to verify correct or override it. In cybersecurity, it attributes anomaly scores to specific network features, so analysts can respond to the right threat. In defense, explainability decisions are essential for rules of engagement and accountability. In finance, regulations like Basel III and GDPR require that credit decisions should be explained to the customers. So that means it is not merely the prediction, it is optimal and explainable decision. So where is this field going right now? What are the research frontiers? Basically, there are 5 domains stand out. That is explainable reinforcement learning. How do we justify a sequence of decisions made by an agent over time? Graph XAI, where how do we explain predictions on relational and structured data? Like molecules or social networks, like our Facebook is a big social network, then how the graph explainable AI can be applied to that. Causal AI, that is moving from statistical correlation to structural causal models. Then neurosymbolic AI, it combines the pattern recognition of neural network with the logical reasoning. And then verifiable AI, where we produce formal machine checkable proof that an explanation is correct. So that means trustworthy AI equals accuracy plus explainability plus robustness and fairness. So we started with f starting from x to y, the simple equation which we opened in the starting. So mathematics tells us how to build that function through linear algebra, optimization, probability. Mathematics tells us how to explain it through game theory, information theory, and causal interference. And mathematics also tells us how to trust it through fairness, constraints, and robustness bounds. So mathematics is not merely supporting explainable AI, it's the foundation that enables intelligent systems to become transparent, trustworthy, and accountable decision makers. That's all from me. Thank you.
Thank you, Dr. Sarika Dyan, for the nice lecture. Any questions? Anyone? Thank you. Thank you so much.
Thank you, ma'am.
The next speaker is Professor Pankaj Kumar from MA University, HP, India. Maharaja.
सही है ना? एक मिनट। ओके।
मुझे बताइए ना आपकी बेटी अपनी।
जी सर। ये ना
जी सर, आप इसकी जरूरत पड़ेगी क्या?
इसकी जरूरत है, आप माइक जो आप कंफर्टेबल लगे वैसे आप माइक पे बोलिए। रूम के लिए तो काफी है इतनी। प्लीज कंटिन्यू।
Good morning, everyone. I am Dr. Pankaj Kumar from Maharaja Agrawal University, Himachal Pradesh. I thanks to organizers and my special thanks to Professor Garola for inviting me to deliver a talk. So today I will discuss bouncing model of the cosmic evolution. So let's first have a short picture of our universe. What is our universe? What the universe have? So let us first discuss about what is the main source of our knowledge. So main source of our knowledge is light. We are seeing everything due to light. I am able to see you. You are able to see me. This is the light. So light is the main source of our knowledge and information, and speed of light is 2.99 multiply 10 to the power 8 meter per second. Light takes only 0.13 second to take a round of Earth. And light from sun takes 8 minutes and 26 seconds to reach Earth. So it seems it is very, very fast on this scale of universe. But if we go further, this is our solar system. Light takes more than 4 hours to reach the last planet, Neptune. Because Pluto is out of the picture now. It is not considered as a planet now. So last planet is Neptune, and it takes more than 4 hours to reach to the Neptune. But this time is also manageable. 4 hours is not very large amount of time. Let's go further. This is our Milky Way, our galaxy, our home. Light year is a distance, not the, it's appears like a distance of time here, but it is the distance measurement, light year. Light year means light takes the distance, light takes 1 year to travel. It's called the light year. So our galaxy is 1 lakh light year apart. Means if light start traveling from one end to the Milky Way, it will take 1 lakh years to cross our own galaxy. So 1 lakh years is a huge time for human civilization. Our civilization is not too old, only 2 or 3 lakhs year old. So 1 lakh year is very huge time for us. Now let's move forward. These are the 2 galaxies. One are Milky Way galaxy, and second is the Andromeda galaxy, which is the major nearest galaxy to our Milky Way galaxy. And these 2 galaxies are 2.5 million light years away. Means 25 lakhs years light takes to reach from one galaxy to another galaxy. And this is the nearest galaxy to the Milky Way. This is the picture of some part of our universe. Every dot you are seeing in this picture is a galaxy. And we have measured billions of galaxies till date. So you can imagine how huge, how vast the universe may be. We exactly don't know. So what is the conclusion from these slides? The universe is mind-bogglingly large. Our knowledge about the universe is less than 1%. We hardly know 1% of our universe. Because everything depending on light, and light have a finite speed. So we are seeing very old picture of the universe. See, suppose you have a telescope which can see Andromeda galaxy, and light reaching to you, that light started traveling 25 lakh years before now, because light takes 25 lakh years to reach us. So you are seeing the picture of Andromeda galaxy, which is 25 lakhs year old. So we are seeing even we can't see the actual picture of the Saturn or Neptune. That will be an older picture. So now we are trying to understand the evolution of this huge universe. There are 2 popular theories, Big Bang theory, and second one is bouncing universe theory. What is the Big Bang theory? This is the picture according to Big Bang theory. There was a bang-like explosion at the very beginning. And everything was created about this after this bang. Universe evolved gradually, and at the present present time, the universe is accelerating. Accelerating means the speed of expansion is increasing according to recent observations. So this is the picture of Big Bang theory. The rest thing is okay, no problem, but Problem is with the bang. Why the everything started from this bang? This is the theory of bouncing universe. Means there was no bang. This is a contraction and evolution type of situation. The universe is contracted to a minimum size and then expanded to its present form we see now. This is the concept of bouncing cosmology or bouncing universe. ये जो ऊपर टाइटल पे लोगो आ रहा है ये हट सकता है क्या? पूरा टाइटल ही problem of Big Bang. What are the problems of नहीं हटे कोई दिक्कत नहीं हट सकता हो तो okay. Thank you. Problem of Big Bang theory. Singularity problem. Singularity problem means at the point where the bang happened, all the physics, all the mathematics doesn't work there. No mathematical rule follow, no physical rule follow. So this is also a problem. This is called the singularity problem. Second problem, how a huge universe can come from nothing. It is also a very huge problem. Why did it started at the particular time? Why not before that? Why not after that? Why to at this particular point the bang happened and everything was created? So these are problems with Big Bang theory. So alternative is bouncing cosmologies. So at the present, there is no well-defined bouncing theory which can accommodate the bouncing behavior and the later stages of the universe, like decelerating phase and after that oscillating phase. But what we do, we assume a scale factor. Scale factor here is directly linked to the distance. So you can say this is a distance. Or we can consider Hubble parameter, which is derivative of scale factor divided by A. So we considered a scale factor A in terms of T, and where the parameter M, alpha and beta, which have some values, M and beta are non-negative values, have non-negative values, alpha is greater than 1. So what is required for bouncing cosmology? The scale factor A must be a finite number. Otherwise, it will be 0, then it will be like a Big Bang type of situation. The scale factor, the distance must be a non-zero value. Universe contact to a non-zero value, then after that it's expand again. It don't come to the zero distance. So if we put t equals to 0 in this value, we obtain at equals to m log a, which is a non-zero value. Thus, it may provide the bouncing universe. But some further requirement are at t equals to 0, the derivative of a equals to 0 means derivative of distance equals to velocity. Velocity is 0. It means it is starting from that point. And second derivative is positive, which is required to have bounce. After contracting phase, if you require again evolution, then second derivative must be a positive value. So we attaining this value. So this scale factor may provide the bouncing cosmology. But for this model to be a good model of bouncing cosmology, we have to discuss further things to ensure this. So this is the Hubble parameter, which is a dot by a. A dot means derivative of a with respect to time. we have plotted the graph of H at the bounds H equals to 0, which is required. Before this, it is have negative values. It means universe contracting from a full evolved universe to a minimum size, and after that it is evolving again. This picture showing this behavior. Next is the deceleration parameter Q, which is defined as A double dot A divided by A dot square. A dot square is positive because it is square. A is distance, it is positive. A double dot. A double dot means second derivative of distance acceleration. If A is positive means accelerating, but it has Q have negative sign. So if Q have negative value, then universe will accelerate. If Q have positive sign, then universe will decelerate. T equals to 0, showing the time of bouncing before negative C prior to bouncing point, and positive P after the bouncing point, what the situation is. So we see the Q is going to a negative value, means it's rushing towards the minimum size, decelerating towards the bouncing point, and after that it's bouncing or evolving. Now observing these behavior of scale factor, Hubble parameter and deceleration parameter, which are directly obtained from the we are considered value of A. Now we are choosing a theory, FRT theory. There are several theories, general theory of relativity of Einstein, FRT theory. We are considering FRT theory and want to discuss how the physical quantities behave, whether they behave in a proper manner or in absurd manner. So we consider a isotropic and homogeneous universe given by the line element 4, and we consider the form R plus lambda T of FRT and obtained equation number 5 and 6. Using these equations and value of A, we considered we will find out the cosmological parameters and quantities and will discuss their behavior. So here, first we discuss the energy conditions. There are two main energy conditions in the universe. Rho means density of the total fluid, and P is the pressure. The sum of rho plus P must be positive for the main evolution of the universe, but at the point of bounce, it must be negative. Otherwise, bounce will not occur. So here we have plotted rho plus P, and we observe that near the bouncing point, rho plus P having the negative value. It means bounce is properly behaving in this model. After that, we observe a positive value, which is well behavior of rho plus P. After that, second energy condition, rho plus 3P. We have the same kind of behavior here also. At the bouncing point, we having the negative value of rho plus 3P, and after that, we have positive value. So it is also behaving according to bouncing model. This is the stability check of the model. Vs squared sound speed. If square sound speed is positive, then we say our model is stable. The perturbation don't evolve exponentially. So we observe in this graph that the values are positive. It means the model is stable. Thermodynamics. Thermodynamics play very important role everywhere, in physics also, in the physics of universe also. Entropy. Total entropy must be an increasing function of time, according to generalized second law of thermodynamics. So we observe after the bounce, we have a increasing or positive value of S dot, and in the previous phase of the bounce, we having the negative value of, because when universe is contracting to a minimum size, the entropy is reducing, the system is going to have more stability, less entropy. That's why entropy is decreasing in the phase previous to the bouncing point. So it is also well behaving. So what is the conclusion? The model we proposed is behaving according to law of the physics which are required to explain the universe. The model is also providing a well-behaved bouncing behavior, contracting to a minimum size, and after that it evolving to the present state. Model is thermodynamically also valid. Model is stable. So this model may present a good model of bouncing cosmology, but we have to do further investigations, like observations are available and very powerful observations are coming nowadays. So we have to test this model using the observation as a future work. So thank you very much.
Thank you, Professor Pankaj, for the nice lecture on bouncing model of cosmic evolution. Any questions? Anyone? If no question, let us thank the speakers for the nice presentation. So the last speaker of the session is Professor A.P. Singh from CU Rajasthan. Professor Avinash Kumar from Jhansi. अच्छा तो मेरे पास में मेरा यहाँ नहीं यहाँ पर ये चेंज मसाला इसका नाम
इसको शेयर करना है, शेयर करना है इसको, शेयर हो गया। निकाल बाद में लोग करा देंगे।
F z is equal to half. That is, I take a point half, it's mapped to 1/4, 1/16, or converges to 0. So any point here converges to 0. Any point on this side, say 2, 4, 16, it tends to infinity. That is, it is converging to infinity. So I have something converging to infinity, a component converging to infinity, a component converging to 0. These where convergence is there, that part it is chaotic. For example, on this circle, is going to converge to 1. And if you observe numbers are over this one. So this type of number will converge and only thing. So if they are now take the image of it. So there